All right, let's go over Horowitz and Hill's coverage of differentiators. Let's start from the fundamental equation for capacitors, where we see that the charge on a capacitor is equal to the capacitance times the voltage across it. And Horowitz and Hill tells us that the dynamic version of this is that if you differentiate both sides, the current through the capacitor is equal to the capacitance times the change of voltage across it. Okay, we're going to then draw a specific example of this. So here's our circuit. We have a V in, and that creates a current, which charges up a capacitor. And so just to be specific to this particular case, we write that the current through the capacitor is equal to the capacitance times the rate of change of the voltage into it with respect to time. The problem here is that we have no way of measuring this current. It's the current here that is proportional to the rate of change of the input voltage, and we don't have a way of getting at that current directly in the circuit I've drawn. So let's draw a similar circuit that will provide us a way of getting the rate of change of the input voltage. So here I've drawn a slightly altered circuit. I still have the capacitor, but now I have this resistor. And so, of course, the current is proportional to the voltage across this resistor. And so that should give me a handle on this current that's proportional to the rate of change of the input voltage. Okay. So now, if we're going to write out what the current is equal to, we have that the current is equal to the capacitance, and it's dV dt. But the problem now is that instead of just having the dV in dt that I was hoping to get at, I also have a dV out dt, right? Because it's the rate of change of the voltage across the capacitor, which is V in minus V out. And so I've got this extra little piece to deal with now. And all of that, of course, is equal to this current, which is just the same as V out over R is also equal to this current. Okay, so that looks promising. Let's see what we can do next. Well, I could imagine bringing this C over to the other side, and then when RC goes down, V out over RC goes up, which means there's going to be a big difference between dV in dt and dV out dt. That's the only way I'm going to get a big thing on the right-hand side of the equation. So if I make RC small, then I can get this situation where dV in dt, which is what I was really hoping for the whole time, is much larger than dV out dt, which is the thing I'm not as interested in, but need in order to make any kind of measurement at all, right? I need to have a voltage across that resistor. Okay, so let's go to, let's rewrite this and continue our line of reasoning. So there, I've rewritten everything. And we have that under these circumstances that we just discussed, when dV in dt is much greater than dV out dt, then V out from here, V out is equal to R, I multiply the R to the other side, R times C, there's the C, dV in dt, about equal to. So now here I have what I was hoping for. I have that the output voltage is proportional to the rate of change of the input voltage. That's my differentiator, provided I have this condition that dV in dt is much greater than dV out dt. Okay. So now, if this is true, that dV in dt is much greater than dV out dt, then the dV out dt is kind of like the error, right? dV in dt is this whole rate of change of the voltage across the whole circuit, which is equal to the dV cap dt plus the dV resistor dt, right? And or dV out dt across the resistor. So again, if that dV out dt is small, then my dV in dt is very close to dV cap dt. And that is about all I need to say about that.